Good morning to everyone. Today I go to the unit 2 electrochemistry and corrosion. Electrochemical cell and its types electropotential, origin, oxidation and reduction potential. First introduction part. Electrochemistry is a branch of chemistry. It deals with the chemical reaction produced by passing electric current through an electrolyte or production of electric current through a chemical reaction. Conductors. Conductor is a material which allows free flow of electricity. Example, all metals, graphite, fused salt, solutions of electrolytes. Non-conductors, another name of insulators. Types of conductors. Metallic conductors, the solid material which conduct electric current due to the movement of electron from one end to the other end without producing chemical reactions. Example, all metals and graphites of metallic conductors. Second one, electrolytic conductors. The conducted electric current due to the movement of ions from one electrode to another electrode in solution or in fused state. This process is accommodated by chemical reactions. Cell terminology. Current, flow of electrons through a conductors. Electrode is a material. It is a rod, bar, strip which conduct electrons. Anode, electrode at which oxidation occurs. Cathode, electrode at which reduction occurs. Electrolyte, water soluble substance forming ions solution and conducts electric current. Anode, compare the term of cell in the cell terminology. Seventh one, cathode chamber component of the cell in which the reduction half reaction occurs. It contains the cathode. Eighth one, half cell. It is the power of a cell which contains a electrode dipped in electrolyte. If oxidation occurs in this half cell, then it is called the oxidation half cell. If reduction occurs at the cell, it is called the reduction half cell. Ninth one, cell. Device consisting of two half cells. The two half cells are connected through one wire. Last one, salt bridge. Contains solutions of salt bridge. Salt bridge mixed solution potassium KNO3 and NH4NO3 that literally serves as a bridge to complete the circuit, maintain electroneutrality of electrolyte and minimize for precise measurement of potential as a salt bridge used. Types of cells. A cell is a device consisting of two half cells. Each half cells consist of electrode dipped in electrolyte solution. The two half cells are connected through a one wire. It is a difference between electrolytic cell and electrochemical cell. First one, electrical energy is converted into the chemical energy. It's called electrolytic cell. Example, electrolysis, electroplating. Electrochemical cells, chemical energy is converted into electrical energy. Example, Daniell cell. Anode carriers of positive charge, anode carriers of negative charge. Cathode carriers of negative charge, cathode carriers of positive charge. Electrons are supplied to the cell from an external resource. Electrons are drawn with the cell. Amount of electricity is measured by coulometer. EMF produced is measured by potentiometer. Extent of chemical changes is governed by the Faraday's law. EMF of the cell depends on the concentrations of the electrolytic and the nature of the cell. Electrolytic cell examples, electrolysis of HCl is a bridge of the platinum electrodes dipped in salt bridge. Mechanism, anode 2 chlorine gives Cl2 plus 2e oxidation. At cathode 2H plus 2e minus gives H2 reduction reaction. The electrochemical cells is example Daniell cell. This is a diagram of the anode and cathode of salt bridge that zinc strip in the anode, that is passing of chlorine ions to K plus ions. Zn reactive to Zn2 plus 2e minus at anode reaction. Cu2 plus 2e minus gives Cu is a cathode reaction. It is a net cell reactions. At anode, oxidations of zinc to zinc ions place with liberations of electrons. At cathode, reductions of the Cu2 plus to Cu place by the acceptance of electrons. The electrons liberated in the oxidation reaction flow through external wire and are consumed by the copper ions at the cathode. Salt bridge. It consists of a U-tube containing a saturated solution of KCl or NH4 twice NO3 or agar-agar cell. It connects to the two of cells. Representations of cell diagram. A galvanic cell consists of two electrodes, anode and cathode. Anode is written as the left hand side of the cathode as the right hand side. The anode is written with the metal first and then electrolyte, which are separated by Voltonic line. Example, Zn bar Zn2 plus or Zn bar Zn zinc sulfate. The cathode is written by the electrolyte first and then the metal. Electrode potential. When a metal is placed in a solution is own salt Mn plus, one of the two processes of possible. Metal atoms go into solution in the form of ions. M gives Mn plus Ne minus. It is oxidation reaction. Metal ions from the solution may deposit metal. Mn plus Ne minus gives M. It is a reduction reaction. Example of zinc reacted with Zn2 plus 2E minus, Cu2 plus 2E minus gives copper. It is a electrode potential. Zinc is a electrode, zinc sulfate is a cathode, copper electrode is a copper sulfate solution. A potential difference created between metal and electrolytic solution. This is called electrode potential. Thus, the tendency of the electrode to lose electrons is called oxidation potential, and tendency of electron to gain electrons is called reduction potential. Single electrode potential, capital E, it is the tendency of a metallic electrode to lose or gain electrons when it is contact with a solution of its own salt. Standard electron potential E naught, it is the tendency of a metallic electrode to lose or gain electrons when it is connected with solution if it is own salt of 1 m molar of concentration at 25 degrees centigrade. The measurement of single electrode potential and its applications of electrochemical series and its application. Measurement of single electrode potential. It is impossible to evaluate the absolute value of single electrode potential using reference electrode. Reference or standard electrode. The potential of unknown electrode can be measured by coupling it with other electrode called reference electrode, whose electrode potential is already known. Example, standard hydrogen electrode, standard calomel electrodes. Standard hydrogen electrode SHE, it is also called primary reference electrode because the potential developed by this electrode is liberally fixed as 0. H2 gas reacted with 2H plus 2E minus. It is a secondary hydrogen electrode. Examples of diagram. It's a platinum electrode added that H2 gas is passed through H2. The salt bridge is attached. Construction. How to construction? It consists of a platinum foil that is connected with a platinum wire sealed in a glass tube. The platinum foil is dipped in 1 molar concentration of HCl. H2 gas is at 1 atmosphere atm atmosphere pressure is passed through the side of glass tube. The standard electropotential of SHE is arbitrary is fixed 0. Limitations of drawbacks of single electrode potential. It is difficult to get pure hydrogen gas. This process of hydrogen is to be kept 1 atm all the time. It is difficult to set up transport. Hydrogen gas reduces many ions like Ag plus and affect compound of mercury, silver, etc. A large volume of test solution is required. It cannot be used in solutions of reduction system. The solution may poison platinum surface. The standard calomel electrode potential SEE, it is a secondary reference electrode. Glass tube containing pure mercury at the bottom over the which mercurous chloride is placed. The remaining portion of the tube is filled with saturated solutions of KCl. The bottom of the tube is sealed with platinum wire. The side tube is used for making electrical contact with a salt bridge. Mercury Mg bar Hg to Cl2 KCl is a saturated solution. E naught value is equal to 0.2422 volt. Is a diagram of saturated calorimeter electropotential. It is KCl value of 0.1n equal to 0.3335 volt. 1n solution is equal to 0.281 volt. Saturated to 0.2422 volt. The mercury reacted with the chlorine to form mercurous chloride plus 2 electron. Mercurous chloride reacted with 2 electrons to give 2 mercury and chlorine. Measurement of single electrode potential as a reference electrode. It's one of the saturated calorimeter electrode. It's a diagram of saturated calorimeter electrode. Mercurous chloride reacted to mercury plus Cl. The EM of the cell is measured using potentiometer. The volume of E cell equal to 1.0025 volt. It's a platinum wire. Calorimeter electrode is there in U-tube, and zinc electrode is another beaker. Zinc ion is converted Zn 2 plus ions. E is equal to E naught right side minus E naught left. E equal to E naught cell minus E naught zinc electrode. E naught Zn is equal to E naught calorimeter electrode minus E naught cell. Electrochemical series and EMF series is a diagram of potential volts equal to reduction of reactions. Significance of EMF series and applications of electrochemical series. First one, the calculations of standard EMF cell. We can calculate the standard of EMF of cell if it is the standard electrode potential. Values are known as E cell equal to E right hand side of electrode minus E left hand side electrode. Another one, relative case of oxidations of reduction. Fluorine has higher positive value standard electrode potential plus 2.87 volt and so higher tendency for reduction. Lithium has highest negative value minus 3.02 volt and so higher tendency of towards oxidation. Displacement of one element by the metal. Metals with the lower reduction potential will displace metal with a higher reduction potential from their salt solution. Copper will displace silver from its solution. Example, Z10 minus 0.76 volt will displace copper plus 0.34 volt from its solution. Zn plus CuSO4 gives zinc sulfate plus copper. Determination of equilibrium constant K for a reaction. Standard electrode potential are used as a determination of the equilibrium constant. Hydrogen displacement behavior. Metals with a negative reduction potential, metals placed above H2 in the EMF series will displace in a hydrogen from dilute acidic solution. Example, Zn minus 0.76 volt will displace H2 from dilute acids, whereas silver 0.8 cannot displace. Zn reacted with sulfuric acid to form zinc sulfate plus H2. Ag plus reacted with sulfuric acid to form no reaction. Predicting the spontaneity of redox reaction. In E naught of a cell is positive, the reaction is spontaneous. If E naught if a cell is negative, the reduction is not feasible. Nernst equations for electrode potential. The potential the nature of the metal or element, temperature and the concentrations of the electrolyte, the functional dependence of potential of any electrolyte system on these factors of given by Nernst equation. E is equal to E naught plus RT by NFF log Mn plus. Potential involves from the interconversation between chemical and electrical forms of energy. The equations pertaining to these two forms of energy is delta G is equal to delta G naught plus RT ln K, where delta G, delta G naught, K and R are respectively the free energy change for any chemical to electrical energy conversion process is given by the equation. Delta G equal to minus NEF, where E is the potential of the electrode system, F is a Faraday's constant is 96496 coulombs. In N is the number of electrons transferred between the element and ion which are equilibrium. Combining equation 1 and 2, we get minus N F E is equal to minus N F E naught plus RT ln K. where E naught is the standard electrode potential of the electrode system. That is E is equal to E naught plus RT by NF ln Mn plus, where A is the activity of the species. The activity of a homogeneous is a uniform solid is taken as unity that of the electrolyte expressed in terms of the concentrations and that gas expressed in terms of pressure of the gas. Equation 4 can be written as E is equal to E naught minus RT ln N of to AM plus, or where Mn plus is the concentration of the electrolyte metal ion in the solution. Substituting the values of R equal to N.38.314 joules, F equal to 96500 coulombs, and introducing factor 2.303 to convert the natural logarithms to Coleman logarithms. Equation 5 becomes E is equal to E naught plus bracket 0.059 bar n log Mn plus. Equation 5 and 6 are the two forms of Nernst equation, which gives depends of electrode potential on the factors mentioned. Applications. It is used to calculate the electrode potential of unknown metal. To know that EMF polarity of electron is electrochemical cell, the corrosion tendency of metals in a given set environmental. Corrosion introductions, types, mechanisms, and dry and wet corrosion. Corrosion is defined as the gradual destruction of metals or alloys by the chemical or electrochemical reactions with its environment. Causes of corrosion occurs. Most of the metals, except noble metals, naturally exist in a combined form. During metallurgy, the metal are extracted from their ores by reduction process. In the pure metallic state, the metals are unstable and considered to be in the excited state. Therefore, the extracted metals have a tendency to go to thermodynamically stable state, which is otherwise is known as corrosion. Thus, corrosion is a process reverse of extractions of metals. Is a diagram of metal gives corrosion oxidation to metallic compound plus energy. Metallurgy reduction is equal to metallic compound gives metal. Consequences of corrosion. The efficiency of machine will be lost due to the loss of useful properties of metal. The product gets contaminated due to corrosion. Increases in maintenance and production cost. Preventive maintenance like metallic or organic coating is required. Toxic products are released. Types of corrosion. Types of corrosion based on the environment. Corrosion is classified into two types. First one, dry or chemical corrosion. Second one, wet or electrochemical corrosion. Dry or chemical corrosion. It is due to the direct chemical attack on metals by atmospheric gases such as oxygen, carbon dioxide, hydrogen sulfide, etc. It follows absorption mechanism. Corrosion product accumulated in the same spot of corrosion. Examples: trainings of silver in H2S gas, actions of tri-HCl or iron surface. There are three main types of chemical corrosion. Oxidation corrosions or corrosion by oxygen, corrosion by hydrogen. Oxidation corrosion is the diagram of oxidation. M reacted with Mn plus Ne minus oxidation reaction and metal to metal oxide surface. At the oxide of scale environmental interface, NO2 plus Ne minus gives NO2. Overall reaction M plus NO2 gives Mn plus NO2. The nature of oxide films formed on the metal surface plays an important role in oxidation occurs. Corrosion. Nature of oxide layer and the future course of corrosion. Stable. The oxide layer formed in some cases stick firmly to the parent metal surface. Such layers is naturally do not allow penetrations of oxygen to the unclearing metal surface and thus act as protective films. Example: Al, SN, SBP, Cu, etc. Unstable. In case of some metals, element or uncombined state is naturally more stable than the combined state, such as oxide, sulfate, sulfates, etc. Metal oxide reacted to form metal plus oxygen. Only forward reaction is forwarded, so oxidation corrosion is not possible in those metals. Example: silver, gold, and platinum. Volatile. In some metals, the oxide layers formed are volatile. They have the metal surface as soon as they form. That means the fresh metal surface is kept exposed all the time further attack. This make corrosion continuous or repeat. Example, metal oxide. Building Bedworth rule. An oxide layer is protective or non-porous if the volume of the metal oxide formed as at least as a great as the volume of the metal which it is formed. Protective or non-porous, example Al, Sn, lead, copper, etc. An oxide layer is non-protective or porous. The volume of the metal oxide formed is less than the volume of the metal from which it is formed. Wheat M1O2. Non-productive porous, example alkali metals, lithium, sodium, potassium, etc. Alkaline earth metal, magnesium, calcium, silicon, etc. Corrosion by hydrogen. Atomic hydrogen can more easily penetrate steel and other metals than molecular hydrogen, which is chemically more active. Hydrogen embrittlement. At ordinary temperatures, some reactions production atomic hydrogen will attack metals and reduce their strength. Example, aqueous solutions of H2S liberated atomic hydrogen to iron surface. Fe plus H2S gives FeS plus 2H. Decarborization. At high temperatures, atomic hydrogen is produced by thermal dissociation. H2 gives H plus H. 4H plus in steel gives methane. The gas collects in a gas and avoids causes blisters and fizzes. Consequently, the metal becomes weak. Liquid metal corrosion. This is brought about by chemical action of following liquid metals at high temperatures over solid metal or alloy. The corrosion involves either dissolutions of solid metal by a liquid metal or internal penetrations of the liquid metal into the solid metal. Example, coolant or sodium metal leads to corrosion of cadmium in nuclear reactor. Wet or electrochemical correction. This type of corrosion occurs metal in contact with the electrolyte or varying concentrations of oxygen. Two dissimilar metals or alloys impressed in partially dipped in solution. At anode, oxidation takes place loss of electron. At cathode, reduction takes place gain of electron. That is involves the flow of current between anodic to and cathodic areas. Mechanisms of electrochemical corrosion is a diagram of electrochemical corrosion. Acetic reaction 2H plus 2E minus gives H2. Basic reaction O2 plus 2E minus plus H2 is equal to OH minus. The overall reaction ferric reduced to hydrogen to form Fe plus H2. Absorption of oxygen, rusting of iron, types of corrosion. This type of corrosion occurs when metal comes in contact with a neutral or alkaline medium. Is a diagram of the absorption of oxygen. Anode reaction Fe gives Fe2 plus 2E minus. Cathode reaction O2 plus 4H plus 4E minus gives 2H2O. Overall reaction ferric reacted with hydroxyl gives ferric hydroxide, ferrous hydroxide, and ferrous hydroxide plus reacted with oxygen to form water to give ferric hydroxide, rust ions. Types of electrochemical corrosion. First one, galvanic corrosion of bimetallic corrosion. It is the diagram of bimetallic corrosion. Zinc as anode, copper as cathode. Zinc more active. It a reduction equal to value minus 0.76 volt. Cathode E not reduction volt. It is a plus 0.34 volt. Zinc and copper couple. Zinc act as anode and copper acts as cathode. Steel screw in a brass of marine wires. Differential aerations or concentrations of cell corrosion. This type of corrosion occurs when metal is exposed to varying concentrations of oxygen or any electrolyte. This is diagram of differential aeration. At anode is aerated part of corrosion occurs M gives M2 plus 2E minus. At cathode more aerated part of OH by ions produced. More oxygenated part is cathode, less oxygenated part of anode. Pitting corrosion. Pitting is a localized attack resulting in the formation of hole around which the metal is relatively unaffected. The mechanisms involved is differential aerations of corrosion. This is the diagram of fitting corrosion. Water draft anode is a less O2, cathode is a more O2. Fe gives Fe2 plus 2E minus anode reaction. 1 by 2 O2 plus 2E plus water to give 2OH cathode reaction. Overall reaction ferric reacted with 1 oxygen plus water to give ferrous hydroxide. Water line corrosion. It is diagram of water line corrosion. Fe2 plus 2OH minus Fe ferrous hydroxide, highly oxidated part of cathode, poor oxidated part of anode. Difference between chemical and electrochemical corrosions. Chemical corrosion of dry corrosion, electrochemical of wet corrosion. Chemical corrosion. It occurs in dry condition. It occurs in the presence of moisture or electrolyte. It involves the direct chemical attack by the metals by decreases dry cases. It involves the setting of large number of electrochemical cells. Corrosion products accumulations in the same spot of corrosion. Corrosion occurs at anode product either cathode. Corrosion is uniform throughout the surface. Corrosion is not uniform, which depends on anodic and cathodic. It follows absorption mechanism. It follows mechanism of electrochemical reactions. Factors influencing the rate of corrosion. The rate of extent of corrosion depends on nature of the metal and nature of the environment. Nature of the metal, positions in galvanic series, over voltage, purity of metal, relative area of anode and cathode, nature of oxide film, other surface film, nature of corrosion product, physical state of metal. Position in galvanic series. First one, the magnesium alloy, zinc, ferric, nickel is the active anode. Lead, hydrogen, copper, silver, platinum is a noble cathodic over voltage. If a hydrogen over voltage of cathodic metal is a very high, corrosion rate is lesser. When the voltage is circuit of part of it raised above if upper design limit over voltage 1 corrosion. Over voltage of a metal, that is when zinc is dipped in sulfate NH2SO4, the hydrogen over voltage is 0.70 volts. Purity of metal. The 100% of pure metal will not undergo any types of corrosion. Relative area of anode and cathode. Corrosion is served if anodic area is smaller than cathodic area. Fourth one, nature of oxide film. The nature of surface film formed decides the extent of corrosion. Nature of corrosion product. The corrosion product formed is soluble in corroding medium. The corrosion rate will be greater. Similarly, if the corrosion product is volatile. Example, MnO3 plus SnCl4 both are volatile, corrosion rate will be faster. Physical state of metal. The rate of corrosion depends on physical state of metal, that is grain size, stress, the orientations of crystals. The smaller of the grain size of metal or alloy, greater will be solubility. Nature of the environment, temperature, humidity, presence of impurity atmosphere, presence of suspended particles, nature of the ions present, effect of pH. First one, temperature. The rate of corrosion is directly proportional to temperature. Humidity is nothing but the greater is the humidity, the greater is the rate of extent of corrosion. This is to the fact that moisture acts as solvent O2, H2S, SO2 and NaCl etc. resulting in electrochemical cell. Third one, presence of impurities in atmosphere was presence of gases like CO2 and H2S, SO2 and fumes of HCl, H2SO4 makes the environment acidic. So corrosion is accelerated. Fourth one, presence of suspended particle. It's also the environment contains chemically active particles, sodium chloride, ammonium sulfate. They are absorb moisture and act as strong electrolytes. So rate of corrosion is very high. Nature of ions present. Presence of silicate anion, the medium leads to the insoluble products, silica gel, which prevents corrosion. Presence of Cl ions is electrolyte destroys the protective films that engage corrosion. If ammonium salts are present in corroding medium, that will be lead to corrosion of many metals. Effect of pH. Generally, acidic medium is more corrosive than alkaline medium. The corrosion of ion of oxygen free water is very slow up to pH. Corrosion control selection and designing of material, sacrificial and impressed current cathodic production. The corrosion process depends on the metal and the environment. So control measures of the aimed at the metal and environment. That is metal based control measures and the environment based of control measures. Metal based control measures proper choice or selection of metal or proper design cathodic production. Proper choice of selection metal or proper design. Before fabrications of equipments, proper selections of metal or alloy have to be studied according to the environmental conditions. Corrosions can be avoided by replacing the metal part of plastics, rubber, ceramics, etc. as far as possible. Metals not affected by stainless steel HNO3, steel, concentration of sulfuric acid, Ti, hot acids and alkalis. It's a diagram of paper choice of selections of metal. Proper design is a diagram of bird design is a poor design. It's a proper design, second one part. It's a good designs or best designs are well joined. Design play an important role of corrosion control. Important designing principles are avoid direct contact to dissimilar metals of using adhesives. When two dissimilar metals are in contact, the anodic part should have large area of the cathodic part. Care must be taken in designing an equipment so that a liquid can be drained off completely. Ceramic corrosions and caustic embeddment can be prevented by avoiding hair cracks, caps and protecting parts. Single crystalline solids avoid intercrystalline corrosion. Stress corrosions can be avoided by heat treatment technique, annealing. Heterogeneity is reduced by using pure metals, which decreases corrosion rate. Cathodic production. In cathodic production, the corroding metal is forced to act as cathode. Sacrificial anodic production. Second one, impressed current cathodic production. Sacrificial anodic production is diagram of magnesium rod. Mg gives Mg2 plus 2E minus. It is the advantages, no need of external power supply. Installations and maintenance cost is very low. Limitations, not suscited for large objectives due to the limited driving potential. Uncoated parts of cannot be uploaded. Impressed current cathodic production. In this method, on impressed current, it's applied the opposite direction of the corrosion current of nullify, which convert corroding metal from anode to cathode. It's a diagram of impressed current cathodic production. Steel pipe gives reactor to DC current of negative one electrode and bag fill of mix of gypsum. Advantages, larger objectives can be protected due to large driving voltages. Uncoated part of can be protected. Limitation, larger installations cost. Thank you.